Okay, hello and welcome everyone to today's morning session. Our first speaker is Elliot Paquette from McGill University, and he's going to tell us about homogenization of stochastic gradient descent in high dimensions. And before we start the talk, I would like to remind everyone that after this talk, there will be a group photo during the coffee break, and so please stick around for the photo. And after that, the next talk will be at 11:15. So over to you, Elliot.
Thank you very much, Subro. And thank you very much for the opportunity to be here, organizers. It's a real pleasure. So I'm going to talk about a high dimensional limit of something. It's an algorithm. It's a stochastic gradient descent. I just want to situate precisely or a little bit what I'm talking about. So basically, I didn't mention who this is with. So this is with this wonderful group of people. So that's Courtney, that's my wife. That's also my research partner, Courtney Paquette, also Jeffrey Pennington and Ben Adlam, who are at Google. Yeah, so I wanted to situate just a little bit what this is about. So this is about high dimensional optimization. What do I mean by that? I mean that you want to solve a minimization problem. You want to run an algorithm to solve the minimization problem. And the problem is in some sense large in various ways. So most or a large class of minimization problems can be written like this, where you would like to minimize over some state X, some loss L of X, and the loss typically takes the form of 1 over n, the sum of some Fi of X. And each of those Fi should be interpreted, for example, as how well, or the loss due to a single data point of some sort of statistical problem. So these Fi's would be some kind of random functions. And it's high dimensional, meaning that both n and d are large. So I won't say exactly what the functions are here. In a second, I'll just make these quadratics, random quadratics. Both n and d are being large is kind of what's really relevant for interesting optimization applications. So there's some sort of very loose empirical work that shows that as you grow the size of large statistical models, the parameter count d is growing frequently very close to proportionally with the number of data points. Though there's some sort of maybe polynomial laws, and this x to the 1.01, which is the relationship of that n and d observed empirically here. There's different estimates for what it could be, like 1.3, 1.5, whatever. Anyway, it's not well posed what exactly it should be, but both are growing. That's the point. Okay, and then the purpose of this type of research is to give informed statements about what algorithms are doing on such a problem as the size of the problem grows, both n and d. So I'm going to talk about sort of the most basic algorithm that comes in this setting, in the most basic setting, which is the least squares problem. And there's actually something mathematically interesting to say here. So this will be the optimization problem. It's going to be the minimum over x of 1/2 of ax minus b norm squared. That's the Euclidean norm squared. And that's going to be added to some extra regularizer parameter delta over 2 norm x squared. And I want to think of A as random. Mathematically, I'm not going to need to take it to be random. So I'm going to enforce some deterministic conditions on A, which are inspired by what would happen in a random case. The algorithm, in fact, can finally just be written like this. It's absolutely the most basic algorithm. You want to update your state x, and what you do is that you choose a data point. So you take a standard basis vector E, ik. So ik is the choice of basis vector. And you update xk plus 1 by being xk minus, this turns out to be the gradient in the direction of one row of this norm up here. Gamma k is a step size parameter. For all intents and purposes, I've included it, but you could just take gamma k to be 1 here. It doesn't really play an important role. Okay, so there's a couple of things that I want to show you. So the first I'm going to describe an effect where what happened to delta? Delta, oh, you're right. This was delta is equal to 0. Thank you. Delta is not going to play a big role in anything that I say. You can take delta to be 0 throughout the talk. Yeah, so I'm going to make a couple of main points here. So the first is that when you make the dimension large, there's a way to replace this this Markov chain by an SDE, and the SDE is going to be it's a little bit different than what the typical type of diffusion approximation in two ways. The first is that the updates of this are not becoming small. So the updates of this are actually large. I'm not going to send gamma to 0. That's one of the typical ways to make SGD comparable to a diffusion, is to send the step size to 0. So the step size is going to be fixed in this procedure. On the other hand, the dimension is going to be large, and that's going to effectively play the role of making things diffuse, so small increments. A second thing is that there's going to be a homogenization effect. So the natural diffusion coefficient that would describe the SDE is not the one that just comes by computing the conditional expectation here. So I'm going to replace the diffusion coefficient by something else. And that by itself, I don't think would be necessarily interesting. First of all, it's possible. But secondly, why is it interesting? Because that greatly reduces the complexity of what this diffusion does in high dimensions. So if you do this homogenization, there is a kind of solvable model that describes the evolution of the loss, and then in fact of the whole state of the process. And I know that this is the math audience, but maybe I'll add at the end a little bit about why that ties back to the original program of how this is interesting for doing something or saying something about optimization. I think it's interesting to note that everything I do here can be actually realized in practice quite easily. So this is an example of an actual least squares problem we ran where we took something called CFAR5M, which is 5 million pictures. We made a classification problem out of it just by trying to do a least squares problem to fit which ones were in which classes. Ran SGD, recorded the losses, and then superimposed what the theory would tell from this setup, and the match is very good. So this type of setup actually can describe a simple real world problem, this homogenization. So that's what these smooth lines are here. Okay. If you don't care for any of the sort of motivations for this, one way just to formulate this problem mathematically is we're taking products of random matrices. So we're looking at a state which evolves like a product of random matrices. The random matrices are of the form identity minus a rank 1 projection. The rank 1 projection has a singular value, which is not going to 0 or anything. So it's at each step you choose a sort of random direction to make an update. And part of the interest here is that the distribution, I mean, conditioned on the matrix A, the random matrices here are independent, but the distribution is some sort of finitely supported distribution in high dimensions. And so I'm giving you some conditions on that distribution in high dimensions where you can say something interesting. Okay, so yes.
So if the delta was not 0,
yeah,
then how?
Yeah, let's see, that's a good question. So I have simplified this in two ways. First of all, I took B to be 0, so that was even before taking delta to be 0. So this is a special case. If I take delta to be non-zero, first of all, do I remember what the Yeah, so this recurrence updates by subtracting delta times xk in the.
So my general question.
We do this for b naught 0 and delta naught 0. Just this particular analogy is only true for. Okay. All right. So the first part. So what do I mean by homogenization? So there are people in this audience who know homogenization much better than me. Try not to make a fool out of myself. I don't think I can exactly mathematically tie this to existing homogenization theory, but there's a very similar effect, or it has a strong similarity. If you were doing a standard diffusion approximation, this is what you would do. You would take this update, you would compute its conditional mean, and you would say that xk plus 1 behaves like xk minus gamma k times a piece of conditional mean. And then if the step size is small and you get some sort of diffusion approximation, well, then you're replacing the randomness by an increment of Brownian motion. So I'll call this the mean. So you would typically need to have all of these things have good continuous limits. So you would have that, well, you scale x as a multiple of time. So you make some sort of speed up by a factor of n here. You assume that your step sizes are coming from some continuous profile. Your means are coming from some continuous profile, and your diffusion coefficients are coming from some continuous profile. And then you would pose that this Markov chain looks like the solution of this diffusion. And this has been done for SGD in a various different contexts. And there's some sort of relatively, well, okay, so there's two results in this direction, which are sort of general in the sense that they work for lots of different SGDs. And there's a recent work which is much more spiritually aligned with what I'm talking about, which is Jagannath, who I don't know if he's here, but I guess we'll be here next week. And they do something which is for a large class of SGD setups, different problem setups. They take high dimensional limits, but it's a type of diffusion approximation. So you assume that your drift and your diffusion coefficient have nice continuous limits. Okay, so in contrast, what I'm doing here is homogenization. The classic sort of homogenization picture is, for example, random walk on a percolation cluster, where the random walk still converges to some kind of Brownian motion or Brownian motion. The point is that the local defects, the statistical defects type sort of average out. So they're happening on a much faster scale than the diffusion approximation is holding. And so instead of getting some sort of messy diffusion coefficient, which would be the actual diffusion coefficient of the random walk on the percolation cluster, you can replace it by actually just the normal or identity diffusion coefficient. One way to see that there has to be a difference is that the actual mathematical statement that you end up proving has to be a little bit different. So in spite of the fact that in law that this is becoming Brownian motion, there might be other things which don't exactly work in a diffusion setup. For example, in a percolation cluster, you have inaccessible parts of the space, so that the heat kernel can't just be in soup norm the transition of Brownian motion. Okay, so that's happening here, and this is the object that represents SGD in high dimension. So this is homogenized SGD. And I want to say what the parts are. So the mean term is just what you would get if you take the conditional mean of SGD. SGD moves in a direction of the gradient by speed gamma. So this is minus gamma grad f of x of t, and f was the original loss, the thing that which we were trying to take the gradients of. This is the part which is maybe a little bit unexpected. So this is the diffusion coefficient. L here is just part of the loss. It's just the part involving the matrix. This Hessian right here is just a matrix A transpose A. So it's just a fixed matrix. I'll say more about this, but this is not the actual covariance of the increments of SGD. So I'll give you a comparison in just a second, or right now. I do want to say something else about this L. Maybe I'll say that in just a second. So how does this differ? So this is the diffusion coefficient of homogenized SGD. You write this out. What you have is just the actual, this least squares, or this L2 loss, and then you have this A transpose A term. This is the actual SGD increment covariance matrix. It has two parts. And basically, this second part is actually just tiny. It's scaled by too many factors of n, so it's vanishing. It's not important. So the real point is that these two things are somehow being, you can exchange one for the other. The actual covariance or diffusion coefficient of SGD is this. It looks like a per element loss. So this AI represents a row of the matrix A, and you take a weighted sum of AI transpose AI by the losses. So these two differ just by the fact that you can decouple decouple the A transpose A from the actual loss, from the full one, and I'll explain why that's interesting. I want to add that these these matrices are almost certainly not close in norm. It's really neither necessary nor sufficient that they be close in norm for anything interesting to happen. It's more that when you test them as quadratic forms, they have the same law as quadratic forms when tested against fixed vectors, which is closer to being important. Okay. And so then I want to formulate a theorem. And there's a lot of bullets here, I know. So first of all, there's assumptions on A and B, and these are interesting assumptions. They're important. I'm going to put them on the next slide. So we have to put lots of assumptions. I'm calling it quasi-random. That's probably a terrible name. I think that all of you will have your own opinions on what they mean when I show them. They're quasi-random because I called them quasi-random because they would be satisfied if you choose a typical random pair A and B with some good motivations. You can check that they satisfy this assumption. Now, the sense of comparison, if I can just go down here, is that if I take the state X and I take the loss of it and I compare it to the loss of this diffusion, and I take some other statistic R, which is another quadratic, which in fact, for the moment, you could just not have it, but for some other quadratic, that this this quadratic and the same quadratic applied to homogenize SGD, that this whole difference is small by something that depends on the dimension. And I've assumed that the dimensions are basically the same, so they're powers of each other. So I'm interchanging D and N freely here. This is on any fixed time horizon, so it's for any length, a finite length of time, sort of held independent of N and D. I'm not telling you what the probability space is here. So these are two different random processes. They could be independent of each other. And if this is still holding, how can it be the case that you take two independent processes and you have them both small by factor d to the minus epsilon? Well, that's only if they're concentrating around their mean. So that's also part of the story here. So implicitly, these are also concentrated around deterministic quantities. So I'm not giving you the sort of CLT, the sort of second order approximation here of how close L of xt, or rather it's the Gaussian approximation around it. Nonetheless, it is important that you actually have this diffusion term. So if you don't look at the diffusion term in x of t, it gives you a completely different answer for the deterministic behavior of L of x. Okay, and what are the assumptions on the matrices? So the assumptions on the matrices are in terms of the resolvents. So I ask that that a couple of different conditions hold on the resolvent. So these are on some fixed contour enclosing the spectrum. So take your spectrum, put a contour around it, and then ask that that some sort of, maybe I look at the second one, where some sort of entries of the off diagonal of the resolvent are small. So A should be supposed to have independent rows. So this is a sample covariance matrix. So it's the covariance matrix in effect of the rows. This off diagonal entry is small, and that's consistent with what you would get if you had sample covariance matrices with independent rows. You need some other things. So the other one is some kind of comparison of on diagonal entries of resolvents to actual 1 over n the trace, which is also similarly satisfied for matrices of independent rows. And then you need some sort of interaction between the target B and this and the resolvent of A transpose A, or AA transpose, excuse me. I mean, this is, you know, there could be easy problematic setups, like if B was simply a row of A, this would be some sort of problem. Or it was highly correlated to a single row of A, this would be out. It's kind of, so it's first of all, it's possible to verify these with not so much effort on various classes of random matrices. It's a little bit entertaining to also check that on some classic data sets, if you actually build this, this type of assumption actually is satisfied. So in fact, I think this is the max off diagonal entry of the resolvent. It doesn't verify the other ones, or it didn't check the other ones. So, you know, there's various things that follow as a corollary of this. So one of the things that follows as a corollary of this is a delocalization statement for the eigenvectors. It's actually more than that. So it's also some sort of averaging statement of the eigenvectors. One of the cases which is the simplest, where you can check that this holds, is if the left singular vectors of A are rotationally invariant. In that case, it's an easy exercise to check that all of those hold. So this is encoding some of rotation invariance of eigenvectors somehow. Yes, please. Typically, if you're doing a statistical application, then it would be the randomness of the data that you're fitting. Though I'm not actually. No, I mean, if you suppose that you have sampled from some distribution. Okay, so, but there's also, let me also emphasize, A is not random. A is just something that satisfies these. Random things do satisfy these. But I would suppose that, I mean, here, these matrices satisfy them also. So there's plenty of matrices that satisfy them. In fact, I think you have to put some effort to make matrices that don't satisfy them. But yeah, actually taking a matrix and perturbing it, I guess, would generally satisfy these kind of things. Yeah. Okay, so I thought I would give a few ideas of how this goes, of why these criteria appear, how we use them to say something. My slide is a little bit deficient in that aspect. This is my one slide on explaining this. So possibly maybe I say something now and maybe I can come back to it later, but the basic idea is to do some kind of martingale argument. So you have the theorem was formulated, maybe go back to the theorem. The theorem was formulated as a comparison, not of the actual state, X and capital X, but of functions of the state. And those are quadratic functions of the state in this setup. That's a very important assumption. In fact, I would expect that it's not true if you just compare the states, that they're close. That's too much to ask in this sense. So you take a quadratic function of the state and you can develop it. So for the homogenized SGD, you have Ito's rule and you can write it as a stochastic integral. For the actual Markov chain, you just write it as if you were going to show a diffusion approximation. What you end up finding is if you do that for some G, then the system of observables that you're looking at, this one low dimensional statistic, G of X of T, isn't closed in the sense that you look at the first order and second order terms in the Ito expansion and you get other quadratics which enter into the game. There's still quadratics, but control on the difference of G of XTN and G of XT is not enough to show that the terms in the Ito development are also small. So you have sort of a proliferation of terms. You could then control that term that appears in the expansion, but then you would have a new term that would appear and sort of goes out of control. How do you fix it? Well, the key idea is to do something like this. For a given quadratic you're interested in, make a class of quadratics, which are all of the form mappings of X to the quadratic form X transpose, resolvent AA transpose, Hessian of G, resolvent Y AA transpose X. So it's a large class. I mean, it's a class. It's a continuum. On the other hand, with resolvents, you effectively have some kind of finite entropy. You can discretize and you can approximate by finitely many terms. And moreover, using resolvent calculations, you can control other functions using these resolvents. So in a sense, it suffices to look at this sort of effectively finite family of, well, finite, but family with sort of controllable entropy, like the number of a finite approximation you can count how many terms you need in order to do it. Yeah. 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 Exactly. This G is a very nice G. No. Yeah, so then, oh yeah, sorry, thank you. Yeah, so this G is not that G, yes. So this G is yes, thank you. Yeah, so then you have this sort of, you can look at the maximum of the deviation over this class of quadratics, and you can show that that's controls itself. So that's you can develop an autonomous sort of Gronwall argument based off of phi of t. If you control phi of t, you can. Yeah, or even a contour. Choose a contour on some curve in the upper half plane that's controlled in or around the spectrum. And it's a real problem. So if you go around, you use a lower. Okay. And so those conditions, those resolvent conditions that I showed you are just the initial conditions to show that this whole class stays good. And then the argument is to show that it continues to stay good. All right, so that's the short version of the proof. I thought I should also say a little bit about what have you gained by doing this. So I made a big point of saying, hey, look, you don't have to just take the diffusion coefficient that comes out of SGD. You can replace it by this other one. Okay, why? Well, who cares? So homogenized SGD has a nice feature, which is that the diffusion, it evolves by this gradient flow term. And the diffusion term separates as a scalar, which is L of x of t, which is a quadratic applied to x of t, and a fixed matrix A transpose A. Now, in high dimensions, what you expect to happen is that this L of x of t is actually going to concentrate. So it's a quadratic applied to x of t. It's going to concentrate around some deterministic curve. If it concentrates around some deterministic curve, this SDE becomes completely trivial. It's just a fixed gradient term. This is just a fixed shape matrix for the noise. And this is some deterministic curve that describes the intensity of the noise. And that actually means that you can write a self-consistent equation for L of x of t. So L of x of t, you can apply Ito to this. You assume it's deterministic. You can say what L of x of t has to be. L of x of t satisfies a Volterra equation, a convolution Volterra equation. So you can describe it in terms of gradient flow. It looks like this. The solution of the convolutional Volterra equation is some deterministic term, which is the loss of an ODE, plus a convolution term. And it's some KT minus S times psi of S. It's actually kind of entertaining that this is the renewal equation. So in spite of the fact that none of this had to do with renewal theory, it's a very simple non-negative convolution Volterra equation. And because of renewal theory, it's easy to get sort of asymptotic expressions for this. You can pull them out of a book. It's also maybe worth mentioning that there's a type of heuristic understanding of what this does. So one way to describe how this loss, psi of t is the replacement for the loss, is the deterministic equivalent of the loss. This convolution term has two parts. This psi of S you can think of as the rate at a given moment of time of noise production. So SGD is making mistakes as you go. It's producing a little bit of noise. That noise eventually has to be solved for, and it's solved for by the mean behavior of the algorithm. So this KT of S is how much in norm that noise is shrinking over time. And then the fact that it's a convolution Volterra equation is saying that all the noise that you're producing is all just basically orthogonal to each other, doesn't interact whatsoever. So at a given moment in time, you create a new piece of noise, it's going to flow down to zero independently of everything else. Okay. This is the general one. I don't know if we have the stomach for this at the moment, but the main point of this is that if you're interested in other observables so this was, sorry, maybe go down here. The other observable of homogenized SGD, it doesn't satisfy a Volterra equation. It just satisfies an equation which is piggybacked on top of the solution of the training loss. So the training loss enters into it, and omega of t is the loss under gradient flow plus some additional term. Okay. I sort of mentioned it already, but I want to argue that this is a good answer to the problem. So there's a couple things which are hard to get about SGD, which are easy to get about this deterministic problem. I think probably the most significant is that two of the things that optimizers care the most about are when does an algorithm converge and at what rate does it converge. And both of those can be extracted from this type of expression, at least in the case when you have a constant step size. So non-constant step size is more of a problem. So this type of convolution Volterra equation, it turns out, is convergent, provided that kernel has a norm which is less than 1. So you have to be able to integrate this k of t. That integral of the k of t turns out to be just some sort of expression involving the eigenvalues. So you can take the trace of A transpose A squared, A transpose A plus delta I, and that represents sort of the convergence threshold for when this algorithm is convergent. The rate of convergence you can also get from convolution Volterra equations. It has to do with solving what's called the Malthusian exponent problem. I think maybe I have it here. Oh, these are some nice pictures. Anyway, this is this is the picture I started with. So this is just showing that that convolution Volterra equation actually, well, this maybe isn't so convincing, but here's the training risk. This convolution Volterra equation describes the actual evolution of these risk curves. This population risk is so noisy, it's hard to see something. If you average the noise in time, it looks a little bit better. This is without any sort of muddying on top of it. And one other thing is you can get the limiting behavior of this. So if you're interested in the limiting behavior of psi and the limiting behavior of the population risk above it, well, convolution Volterra equations have you can find out what the limit value is. And there's some nice statistical observations about it. Maybe I just conclude. This is the rate of convergence with a couple general comments. So what I showed you was about the fact that you can take basically what amounts to something like a product of random matrices, which are independent but drawn from a discrete finite high dimensional distribution, and you can track the norms of solutions or the application of these products of random matrices to a state in terms of these Volterra equations. The most interesting sort of generalizations of this, which are not done, would be to things like replacing the loss. So just having a quadratic is really, in a sense, a toy problem. So it's really would be nice to have other functions that you're minimizing. So non-quadratic extensions are probably the most exciting way to try to generalize this type of thing. These are the papers, and maybe I'd stop and take any questions.
Thank you, Elliot, for the nice talk. So any questions for Elliot? Yes.
Yeah, so yeah, it's enough to have it on a contour enclosing the spectrum. Having it for all Z, you can actually reconstruct those two pieces of data from each other if you enclose the spectrum. That's maybe the key part. Yeah, by complex analysis magic. Yeah.
Can you somehow say something about the proof of this key idea of how do you control the this phi of t?
This phi t, yeah. Right. So the main point is that, can I write here? It's okay for the tech people. Okay, I don't know. So I'm going to go ahead. So if I take, g of xt minus g of x0, now this is going to be 0 to t of a gradient of g dotted with xt. This is gradient of g evaluated at xt, sorry, plus 1/2. And I'll write this in sort of physicist notation. So you have some kind of expression like this, where you have to, okay. So if you do the same for the discrete term, so you can get an approximate version of this. So it's approximately the same thing. Up to some kind of discretization errors, which are not really the main problem. What you'd like to do then is say that g of xt minus g of xtn, by comparing these two things, is bounded by an integral 0 to t of sort of the difference that you see here, which you'd hopefully like to compare to something involving phi of s, this phi being this phi right here. That basically works. You have to do some resolvent computations and so forth to get there. The other really important point, which is completely missing from this, is that if you actually work out the details of doing the comparison, you need to know that the state vector remains delocalized as you run it. So like the most important technical lemma is that the max on k of this is xtn, that's the time at k remains less than n to the -1/2 plus delta. This type of comparison is relatively straightforward. This type of comparison, sorry, is relatively straightforward, provided you have this as input. So without working out more of the details, I can't explain why. But this, so then this has to be done by a type of bootstrap argument. So the fact that this happens is somehow that if you have good norm control on X and reasonable entry control on X, you can get better entry-wise control on X. You have to do that argument first to make progress.
Any other questions? Okay, so maybe I ask 1 or 2 questions of mine. So can you sort of tell us in a simple way how the, you said that you are working in the high dimensional setting and D and N are both going to infinity together, maybe in proportion to each other. So how does that fact come into play in this whole theory?
Yeah, so
fundamentally, how is that useful?
Okay, so first of all, in this argument, it doesn't really appear. We need D and N to be related by powers, but that's so that we can.
But I believe that it should appear in the derivation of the dynamics.
Yeah, so the dynamics really sort of trivialize if D and N are very separated. And I think the main thing is spectrally what's happening to A transpose. Imagine that you're really doing a sample covariance type of situation, and D and N are not proportional. Then this A transpose A is going to degenerate in one direction or the other to be the true population covariance. well, that would be the direction where n is much bigger than d. If d is much bigger than n, well, then it's really something else. So in fact, I'm not sure exactly what it would be, but in principle, provided the resolvent is delocalized, still works.
This SD structure will be available for any n.
Yeah, right. This is basically a finite ND approximation theorem, in spite of the fact that we didn't make it quantitative and capturing all the constants.
And generally speaking, in SGD, it is popular to take the step size, which is decreasing with the number of steps, right? Like 1 over square root of the numbers. So can that be brought into play here?
Yeah, so some types of decrease fit into this. So if this gamma, so gamma here was on an epoch scaling, so gamma of k was a gamma, imagine that it was a continuous function of gamma of k over n. That's a little bit restrictive. So for example, there's a classic Robbins-Monroe, which is a gamma k, which is 1 over k. That doesn't fit into this framework. This 1 over k type rate in practice is really slow if you have dimension high.
That's only for strongly convex, right?
If it's strongly convex, yeah. Well, no, you can use this always, but it's debatable whether you want to use it always. Strongly convex means you have so much speed that I guess you can be inefficient. In this setup, there's sort of classical diffusion approximations, but they're lower order. So you would have an ODE. It's basically that you end up discretizing gradient flow, and then there's a correction around it, which is smaller, which is I think probably a different SDE.
What about 1 over square root?
1 over square root k. Yeah, it's a good question. I don't know. So I guess it potentially fits like without. I mean, it would be singular if you actually tried to fit it into this framework. So I'm not sure what would happen. I guess because it's so much faster than this, it has a chance of being described by.
Suppose so you did here you discussed one batch SGD, right?
Yes.
So suppose I did mini batch SGD with batch size like a small fraction of the n. So how do you think it will affect the results?
Yeah, so I actually have a separate paper on proportional SGD in this setting. This convolution Volterra will become a discrete convolution Volterra equation indexed.
The sum is over the
sum is over a number of steps. But otherwise, it has a qualitatively very similar feel.
And how does your theory compare with the Jagannath Venaru's Hessiari?
Yeah.
So they are also doing a high dimensional approximation, right?
Yeah, absolutely. That's a great question. So I think that the main difference I would say is that they work in a setting where the covariance matrix is just whatever SGD is giving you. So in some situations, where did I put that? Maybe way back here. This is sort of this setting. On the other hand, the function classes they work with are more interesting. So they don't do just least squares problems. So they have interesting non-convex problems where you can do this type of diffusion approximation. You keep the step size fixed, send the dimension to infinity. But the point there is that you're really using whatever drift and covariance are coming out of the problem. So they're converging in sort of in norm to something.
Do you think your theory can be extended to other, at least convex losses? Or?
That's very much what I want to do. Do I know?
For example, if you modify the function class.
Yeah, so Right, so you modify the function class, and there's a question of what type of statement you're looking for. So if you just want to prove that there's a type of effective SDE that it replaces the high dimensional limit, which describes the high dimensional limit, and I think that that's probably possible. For any sort of explicit solvability, probably that's off the table. Like you wouldn't be able to write a Volterra equation describing the loss or anything like that. Maybe I'm wrong. It's also the case that with more interesting non-convex problems, you have multiple statistics which are interesting. So it won't just be the training loss, which you need to record as a function of time. You have to have other, hopefully finite list of statistics, which you also need to track some sort of overlaps between things, which are also relevant. So there's some examples of simple extensions of this where there seems to be a chance, like a two-layer neural network or something like that.
Okay, thank you. So are there any other questions for? So if not, then let's thank Elliot once again for the wonderful talk. And we will assemble for group photo at some point.